In this video, we're going to look at the softmax output function. This is a way of forcing the outputs of a neural network to sum to 1 so that they can represent a probability distribution across discrete mutually exclusive alternatives. Before we get back to the issue of how we learn feature vectors to represent words, we're going to have one more digression. This time it's a technical diversion. So far I've talked about using a squared error measure for training a neural net, and for linear neurons that's a very sensible thing to do. But the squared error measure has some drawbacks. If, for example, the desired output is a 1, so you have a target of 1, and the actual output of a neuron is 1 billionth, then there's almost no gradient to allow a logistic unit to change. It's way out on a plateau where the slope is almost exactly horizontal, and so it will take a very, very long time to change its weights, even though it's making almost as big an error as it's possible to make. Also, if we're trying to assign probabilities to mutually exclusive class labels, we know that the output should sum to 1. Any answer in which we say the probability that it's an A is 3/4 and the probability that it's a B is also 3/4 is just a crazy answer. And we ought to tell the network that information. We shouldn't deprive it of the knowledge that these are mutually exclusive answers. So the question is there a different cost function that will work better? Is there a way of telling it that these are mutually exclusive and then using an appropriate cost function? The answer, of course, is that there is. What we need to do is force the outputs of the neural net to represent a probability distribution across discrete alternatives, if that's what we plan to use them for. The way we do this is by using something called a softmax. It's a kind of soft continuous version of the maximum function. So the way the units in a softmax group work is that they each receive some total input that they've accumulated from the layer below. That's zi for the ith unit, and that's called the logit. And then they give an output yi that doesn't just depend on their own zi. It depends on the z's accumulated by their rivals as well. So we say that the output of the ith neuron is e to the zi divided by the sum over that same quantity for all the different neurons in the softmax group. And because the bottom line of that equation is the sum of the top line over all possibilities, we know that when you add over all possibilities you'll get 1. That is, the sum of all the yi's must come to 1. What's more, the yi's have to lie between 0 and 1. So we've forced the yi's to represent a probability distribution over mutually exclusive alternatives, just by using that softmax equation. The softmax equation has a nice simple derivative. If you ask about how the yi changes as you change the zi, that obviously depends on all the other z's. But then the yi itself depends on all the other z's. And it turns out that you get a nice simple form, just like you do for the logistic unit, where the derivative of the output with respect to the input for an individual neuron in a softmax group is just yi times 1 minus yi. It's not totally trivial to derive that. If you try differentiating the equation above, you must remember that things turn up in that normalization term on the bottom row. It's very easy to forget those terms and get the wrong answer. Now the question is, if we're using a softmax group for the outputs, what's the right cost function? And the answer, as usual, is that the most appropriate cost function is the negative log probability of the correct answer. That is, we want to maximize the log probability of getting the answer right. So if one of the target values is a 1 and the remaining ones are 0, then we simply sum over all possible answers. We put zeros in front of all the wrong answers, and we put 1 in front of the right answer, and that gets us the negative log probability of the correct answer, as you can see in the equation. That's called the cross entropy cost function. It has a nice property that it has a very big gradient when the target value is 1 and the output is almost 0. You can see that by considering a couple of cases. So a value of 1 in a million is much better than a value of 1 in a billion, even though it differs by less than a millionth. So when you make the output value increase by less than 1 millionth, the value of C improves by a lot. That means there's a very, very steep gradient for C. One way of seeing why a value of 1 in a million is much better than a value of 1 in a billion, if the correct answer is 1, is that if you believed the 1 in a million, you'd be willing to bet at odds of 1 in a million, and you'd lose $1 million. If you thought the answer was 1 in a billion, you'd lose $1 billion making the same bet. So we get a nice property that cost function, C, has a very steep derivative when the answer is very wrong, and that exactly balances the fact that the way in which the output changes as you change the input, dy by dz, is very flat when the answer is very wrong. And when you multiply the two together to get the derivative of the cross entropy with respect to the logit going into output unit I, you use the chain rule. So that derivative is how fast the cost function changes as you change the output of a unit times how fast the output of the unit changes as you change zi. And notice we need to add up across all the j's, because when you change zi, the output of all the different units changes. The result is just the actual output minus the target output. And you can see that when the actual and target outputs are very different, that has a slope of 1 or minus 1, and the slope is never bigger than 1 or minus 1. But the slope never gets small until the two things are pretty much the same. In other words, you're getting pretty much the right answer.